It's my pleasure to present our paper Label-Dependent Lambda Calculus and Gradual Typing at UPSLA 21. This is work done in collaboration with my postdoc Wei Fu and my student Fabian Krause. I'm Peter Thiemann and I'm giving the talk because none of us is able and allowed to attend the conference in person. So much for that. Well, let's start with looking at the label-dependent Lambda calculus. So this is a language with lightweight dependent types. So there is the usual dependent function and pair type, and in addition to that, there are label types, and there is a label elimination construct which takes place on the type level as well as on the value level. So as I already said, it's lightweight and value dependent, so the semantics is based on call by value. Labels are a bit peculiar to this calculus, so they are first-class values, just like symbols. The only thing you can do with them is compare them for equality and use the label elimination in order to distinguish them. There's also subtyping induced by label types and pull through dependent functions and pairs, but we're not going into that for lack of time. Instead, let's have a look at an example. So here's the encoding of records using the label-dependent Lambda calculus. So in this case, a person is modeled by a dependent function that takes an element, a label, which is drawn from the set name, age, or flag, and then it distinguishes the label. If it's a name, then the type is string. If it's age, then the type is int. If it's a flag, then the type is bool. In this case, with this encoding, which you can do with any dependently typed language actually, field access on a person is just function application. Now, so P applied to the name label, just the same as usual. So type checking this means you have to substitute name for X here in the body of the Pi type. So you get case name string, age int, flag bool, and that is convertible to string by just reducing the case. All right, and now we can write code to print a field of a person record, which takes here a label value, which must be one of name, age, or flag. It takes a person and then delivers a string. And the thing to note is that in each branch here, the type of P of X is different. In the first branch, it's name, so it's a string. In the second branch, P of X returns an int, so it needs to be converted to a string. In the third branch, the same happens for bool. Now, as you can see already with this small example, writing types for using person is pretty tedious because, well, this is redundant. Here we name the label set, which we could see from here, and here we have to write the same label set again. Okay, so enters the gradual version of the label-dependent calculus. So generally, gradual typing introduces the dynamic type, which we call star here. It allows a clean transition between dynamically typed and statically typed code without compromising type safety. Only that for the dynamically typed parts, safety is guaranteed by inserting suitable runtime checks. And this enables us to start with fully dynamically typed code before figuring out any sort of tedious types. And this is actually a nice fit for dependently typed systems where types are actually notoriously hard to figure out, or maybe just tedious, as in our example. So let's try to represent a record by a dependent function that now takes a dynamic type as an argument. So this code type checks in the gradual version of LDLC. This type is well defined in that version, and also field access still works the same. Now, moreover, due to the way that our type system is set up, even the application of P, which takes a dynamic typed value as an argument, to a particular label, still type checks and guarantees, in this case, that that name is defined and returns a string. Testament of that is if you apply P to a non-existing label, then this fails to type check. Also, the printing of a person record can be lifted. So now the type of field to string is dynamic to person prime to string. Well, obviously you can now apply person prime to to an X because it has type dynamic, and all the other things work out as well. Now, applying field to string to an H label and P type checks and runs to completion, but in the last line, a gradual typing shows rears its head. So here, if we apply field to string to the label foo and a person record, this type checks, but it fails at runtime because the person doesn't really have a foo field. Okay, so what's our overall approach? So in the first example slide, you've seen the base language, LDLC. So this language has an operational semantics and it comes with a nice algorithmic and bidirectional type system. On the second slide, example slide, you've seen the gradual version of LDLC, which is essentially LDLC plus the dynamic type. Moreover, it has a notion of gradual consistent subtyping, which essentially enables that the dynamic type is compatible with any other type. To make that work, we extended algorithmic type checking, and the language by itself has no semantics, but its semantics is given by translation to yet another language, which I'm going to uncover in a minute. Note that the green boxes here denote the surface languages. These are the languages that are actually accessible to the programmer. So the cast language, which is the translation target from translating GLDLC, this is essentially LDLC plus casts. So it also has the dynamic type, but it has a type cast. But in this language, the dynamic type is not compatible with any other type. So if you want to get into or out of the dynamic type, you need to use the cast. On the positive side, it has an operational semantics, and its typing system is also given by an extension of the LDLC system. All right. Given the brevity of time, I'll only cover some highlights of the paper. I'm inviting you to dig into the paper, so there's really a wealth of material, and there are so many details that I can't really do justice to them during the presentation. Right, to get you in the mood, I need to show you a couple of typing judgments. So bidirectional typing means that we need to look at least at 2 typing judgments. So the first one here is the checking judgment that says check the term M against type B in typing environment gamma. And the other one is type synthesis that says synthesize the type A from term M in typing environment gamma. The color coding, red means inputs to the typing judgment, and green indicates outputs of the typing judgment. Okay, let's dive right into the first highlight. So the first highlight is what I call flexible dependent pairs. So here, here we've got the term former for a dependent pair. Yeah, so it says the first component is the value of the first component is named X. It's the value of M, and X can be used inside of N, as you can clearly see up here. Yeah, so X is available for use in the second component. Now, as long as you have a call by name semantics, this doesn't lead to any problems operationally. But in call by value, you get stuck when you want to prove a subject reduction. So the way out of that, one way out of that, is to introduce a second non-dependent pair construction, which you see here. So essentially there's a reduction that transforms the value of this type to that type at the point where it's appropriate. So see the paper for that. The other one is kind of unveils the secret why we were able to push information through the dynamic type. And this is type narrowing using singleton types. So the first one is type checking of the case expression. So here the head of the case is some X, and we have been able to synthesize the type of X as a singleton type, which means we know the value of X at runtime is L prime. Well, if the label is known, then the type checker just performs the reduction. Now, so it only checks one branch of the case, namely the one belonging to N prime, L prime. If the label is unknown, then the type checker gathers information. So in this case, by exclusion, you can find out that if this rule here fails, then it must be that the case header here is a variable, and this type D here cannot be a singleton type anymore. Otherwise, the EL rule would fire. So in this case, in each branch, we have increased our knowledge about the value of X. So we change the type of X in that branch to the singleton type of the respective branch label. And then we type check this, we synthesize the type of that branch. And remarkably, the same approach also works in the gradual setting. So the rule that I'm showing you here is for LDLC, but the same rule with one tiny change here also works in the gradual setting. And there's some really interesting technical details behind this, but no time. Another highlight is now something in the cast calculus. So the cast calculus is the language that actually is our workhorse at runtime. And one thing that the defining part of the cast calculus is, of course, the cast expression. So we have an expression V, and we want to cast it from type A to type B. But now we have this dependently typed stuff, so types can contain red X's, which means A can contain red X's. And before we can deal with that, before we can execute the cast, we first must reduce the types to head normal form. And this is indicated here with this NA before casting. Now, once we've successfully reduced types to this head normal form, then we can proceed with factoring. And by the way, I've omitted the mirroring rules that work on the right type B here. Now the factoring then works as before. And here the factoring means we factor into a cast to a ground type and then ground type to dynamic type. Ground types are again normal forms, so ground types need not contain cases because they are only needed when the types are closed. When reduction gets there. When reduction gets there to this rule here, well, at that point types are closed, right? Because they're only reducing closed terms. Hence, no case in ground types needed. Okay, finally, let's get to the meta theory. So we've proved type soundness for the cast calculus, which includes type soundness of the original language LDLC. We have shown soundness and completeness of algorithmic typing for all calculi that are involved. And we've been able to establish the static and dynamic gradual guarantees for the gradual language. Right, and this leads me to the conclusion. So we've shown you a lightweight dependently typed Lambda calculus, LDLC, which features a label dependency, which I hope I've been able to explain to you, subtyping, and a fairly special treatment of pairs. Then we've shown you a gradual extension of the label-dependent Lambda calculus. We've established the meta-theory, soundness, progress, and gradual guarantees, and we've shown that type checking here is decidable, including the subtyping. I can only invite you to get further information by reading the paper, and in particular to check out our artifact, which is linked in the slides and also in the paper. So the artifact contains a partial mechanization of the meta theory, which is done in ACTA, and an implementation of the type checker, where you can play with all the fun code that you've seen and cross the saber with the type checker. Well, and with that, I can only say thank you for your attention, and I hope you have some interesting question for us. Bye-bye.